Hypothalamus Artificial Intelligence, HI. It presents companies in the process of digital transformation, its offer of professional services and the supply of algorithms of highly complex multi-problem mathematical models. These services are called Smart Grids, Optimization. Lecture prepared by Engineer Jesus Velasquez Bermudez, Ph.D. Smart Grids. Framework. The concept of the smart grid does not have a single creation date, but is the result of a technological evolution that was consolidated in the mid-2000s. The key milestones of its origin are 2001, the Electric Power Research Institute, EPRI, in the U.S., formally proposed the idea of a modernized grid that would integrate information and control technologies. 2001 to 2002, the Telegistor project was launched in Italy by the company Enel, considered the first large-scale commercial deployment of smart grid technology in homes, installing millions of smart meters. 2003, the Great Blackout in the Northeast U.S. and Canada acted as a catalyst to accelerate research into more resilient and digital grids. Consolidation and official laws date from 2007 to 2009. 2007, the term became official in the U.S. with the Energy Independence and Security Act, which defined the characteristics of the smart grid and established grid modernization as a national policy. 2008, in Boulder, Colorado, the first comprehensive smart grid city was established under Xcel Energy's Smart Grid City project. 2009, the Obama administration boosted development with a massive $11 billion investment through the Recovery and Reinvestment Act. Although the term is modern, its foundations were built decades earlier. 70s, the first automatic meter reading devices appeared, which allowed basic consumption data to be sent to electricity companies. 90s, digital energy systems began to be talked about, and wide area monitoring systems expanded. When the change began. In a regulated environment, generation, transmission and distribution are operated by a vertically integrated company, usually a state-owned enterprise that has a monopoly on the supply of electricity. On the other hand, in a deregulated environment, different parts of the electricity grid are owned by different companies, most of them private, and the electricity markets provide a platform that fosters competition and active consumers. Due to the new power technologies, this liberation of the electricity market has reached the industrial factories that must face this new opportunity. The diagram presents the parallelism between the physical and commercial systems. The diagram shows what an old power supply system might look like. A modern energy supply system is impacted by new power technologies, and by advanced analytics, artificial intelligence, machine learning, and large-scale mathematical programming. Smart grids optimization models. Each smart grid requires a specific decision support system that allows the operator to interact with the entire electricity system. Starting from the original electrical system, a wholesale electricity market. Smart grids were advancing little by little, initially seen as isolated systems. Currently, these electrical systems must coexist and interact with each other. The centralized control of the system focused on the development of assets, hardware and software, for the wholesale electricity system. The emergence and development of smart grids generates a distributed control of the system, in which many islands, which initially operate in isolation, must be coordinated. Technological evolution has given rise to total distributed control, in which multiple types of electrical assets coexist and communicate with each other. Smart grids have generated communities of users, that consume and generate energy and require a broad control system that unites all the production consumption cells that the electricity system has. It is a system like the Internet, where the autonomous communities share physical resources and communicate with each other, which gives greater power to the physical system, but requires more advanced artificial intelligence to manage it. Electric power system asset optimization. Optimizing power system assets has been a critical part of utility operations for many years. The company's business processes, including planning, engineering, operations, maintenance, and customer service, are the primary means for asset optimization. The report examines the state in 2011 of utility asset optimization within the framework of a vertically integrated utility and presents evidence as to why assets were not fully optimized, presenting some of the concepts and practices that have evolved since the early years of smart grids. It then discusses how smart grid processes, technologies, and applications have been leveraged to improve asset management programs, enabling significant improvement in both system asset utilization and human resources. These processes, which are part of an asset management program, depend on the availability of data and the ability of technologies to process that data. These technologies have evolved rapidly, making the basics seem outdated. The presentation focuses on basic and typical concepts of smart grids and their evolution and validity. The Distribution Management System, DMS, represents the main business application for managing the complex and dynamic aspects of distribution operations, as it serves as an integration mechanism to link new smart grid applications with existing and future asset optimization applications. A list of a summary of DMS applications is presented. The great value of the DMS is its ability to display multiple applications and offer operators and users a complete context of various parameters that have historically been separated by processes and technologies. Advanced Metering Infrastructure, AMI, is the integration of smart meters, an integrated two-way communication system, and utility consumer processes, and it serves as the primary consumer interface to the electric system. From the utility's perspective, AMI represents the edge of the network. This edge is where most of the innovation is taking place today. In theory, AMI will provide a path not only for utilities to remotely monitor the energy usage at a very granular level, but also for consumers to receive necessary alerts and price signals for their conservation objectives and/or demand response programs. AMI and the information it provides to the customer service and operations processes will help reduce peak loads, improve the detection, diagnosis, and restoration from outages, and reduce the number of calls and resulting truck rolls required today. It also simplifies the meter reading process and substantially reduces the number of labor hours required by the metering process. Integration of AMI with the other utility processes will also improve their ability to optimize assets. Industry 4.0 Advanced Metering Infrastructure, AMI, represents the evolution of utility monitoring from simple digital recording to a high-speed, edge computing network. It serves as the nervous system for modern smart grids, enabling bidirectional communication between utilities and consumers to manage electricity, gas, and water in real time. AMI in the Industry 4.0 era utilizes a four-layered architecture to process massive amounts of big data. Perception layer, smart meters, digital sensors that record usage at regular intervals, SWAC every 15 to 30 minutes, and can remotely manage services like connect/disconnects. Network layer, secure transmission via technologies such as 5G, RF mesh, power line communication, PLC, or low RAWAN. Middleware layer, MDMS, a meter data management system, MDMS, that stores and cleans raw data, converting it into actionable insights. Application layer, where advanced functions like load forecasting, demand response, and outage management are performed. Industry 4.0 has introduced advanced technologies into the AMI ecosystem. Edge computing and AI, modern AMI systems process data locally at the meter to detect anomalies in real time, reducing latency and bandwidth usage by up to 60%. Blockchain, used to secure energy trade transactions and prevent electricity theft cyberattacks. 5G integration, provides the high-speed, Low latency communication needed for real-time grid automation and integrating distributed energy resources, DERs, like solar panels. Load shifting, or shedding, with smart meters is one of the benefits of AMIs. Most retail consumers pay a fixed price for electricity, regardless of the time of day and/or demand consumed. Therefore, have little incentive to reduce their energy consumption and thus reduce their energy bill while helping electricity companies meet demand. For a long time, the electricity consumer was characterized by an inelastic demand function of quantity relative to price. Thanks to technological advances, demand response, DR, is a mechanism in which electricity consumers voluntarily adjust their usual consumption in response to economic incentives. The main objective is to balance supply and demand to ensure the stability of the electricity grid during periods of stress or high prices. When energy demand reaches critical levels or wholesale prices skyrocket, the grid operator sends a signal to participants, who respond by reducing or shifting their consumption, to receive financial compensation. Some types of DR programs are incentive-based. Customer receives direct payments for reducing their burden when requested during specific network events. Price-based. Consumer adjusts its usage based on rates that vary by time, such as time of use rates or real-time pricing. Manual. Consumer manually shuts down the equipment or uses technologies such as smart thermostats that respond instantly to digital signals. Automated. The consumer uses its own management technologies that optimize the response to digital signals. Key benefits include: for the consumer, it generates new revenue streams and reduces total energy costs. For the grid, it improves reliability, prevents power outages and reduces the need to generate additional expensive energy, which can generate more pollutants. Sustainability, it facilitates the integration of renewable energies, such as solar and wind, aligning consumption with periods of high clean production. One of the goals of demand response, DR, is to reduce the peak load that occurs at certain times of the day in certain regions and lasts from minutes to hours. The peak is characterized by a rapidly increasing load in real time and requires quick response from generating resources that are more expensive to operate. AMI and CS applications are expected to greatly enhance the effectiveness of demand response on reducing peak load. Reducing load during peak load periods is a key tool for optimizing system assets. The smart grid will enable DR to be applied more broadly across the system, but to achieve the desired levels of peak demand reduction, many policy, technology, education, and market information objectives must be implemented in states and regions. The demand response strategy and the smart meters allow customers to choose variable prices depending on the time of day. By looking at the true cost of energy, consumers can respond accordingly by shifting their energy consumption from periods of high price to periods of low price. This process can have the joint benefit of reducing costs for typical consumers and decreasing peak demand for utilities. Information and Communication Technology, ICT, is necessary for the integration of smart grid applications to take full advantage of its functionality for asset optimization purposes. ICT applications address this weakness by deploying service-oriented architecture, with an enterprise-level information bus that allows all related applications and communication technologies to interoperate, so that users have access to integrated processes. Key to this functionality is a data warehouse to manage and host the large volumes of data that come from numerous sources. ICT integrates two types of communication systems. Wide Area Networks, WAN, are large-scale telecommunications networks that interconnect devices, and local area networks, LAN, across long distances, covering cities, countries, or even continents, and Field Area Networks, FAN, are communication infrastructures designed to interconnect industrial devices and sensors, over large outdoor areas, acting as the critical bridge between field devices and control centers. Distributed energy resources, DERs, and the smart grid are expected to encourage the deployment of much larger numbers in the future. DER offers a significant opportunity to optimize assets as they are called upon to contribute to the generation mix and support demand response. The challenge will be to efficiently and effectively operate this large number of distributed and diverse resources. DARE operation is expected to be accomplished through two processes: Distribution Management System, DMS, and Microgrids Operation, MOP. Both are expected to assist grid operators integrate DARE operations to improve asset optimization of grid assets and operate more efficiently. In 2010, the Department of Energy, DOE, established the following description of microgrids. A microgrid, a local energy network, offers integration of DARE with local electric loads, which can operate in parallel with the grid or in an intentional island mode to provide a customized level of high reliability and resilience to grid disturbances. This advanced, integrated distribution system addresses the need for application in locations with electric supply and/or delivery constraints, in remote sites, and for protection of critical loads and economically sensitive development. Distributed energy resources and microgrids operation. Along with utility microgrids, a new consumer system type application has recently emerged, the community microgrid. Community microgrids represent a new level of intelligence and control methodology aimed at creating small areas of control that optimize local assets around community objectives. As the complexity of local infrastructure grows, the microgrid provides the intelligent applications needed to achieve local goals. Microgrids operate in conjunction with the main distribution network most of the time, and only occasionally transition to an island operation. This occurs fluidly when community objectives are challenged in such a way that the intelligence of the microgrid determines that the community would be better served economically, reliably or environmentally as an island. When the challenge is overcome, the microgrid seamlessly returns to grid-connected operations. The community microgrid is continuously looking for the optimal solutions to meet its objectives. Microgrids operating in a cellular structure can simplify the operation of these new resources and allow them to be optimized around the most important objectives for local consumers. Multiple microgrids integrated with a distribution management system, DMS, can simplify and optimize the operation of the distribution system and provide another method to improve its efficiency. Community microgrids become an important part of the system, as they are points of accumulation of a large amount of demand and, now, of electricity generation. Combined Heat and Power Generator, CHP, or cogeneration system, produces electricity and useful thermal energy, heat or cooling, simultaneously from a single, typically on-site, fuel source. By capturing heat that is normally wasted in conventional power generation, these systems achieve over 80% efficiency, compared to roughly 50% for separate heat and power, significantly reducing carbon emissions. Advantages and disadvantages. Advantages: high energy efficiency, 65 to 80%, reduced carbon footprint, lower operational costs, and increased energy independence. Disadvantages: high initial capital investment, requirement for regular maintenance, and the need for sufficient physical space for installation. Common technologies used in CHP systems include reciprocating engines, combustion turbines, and steam turbines. They can be configured to operate in parallel with the grid or in island mode, providing critical backup power. Home energy management, HEM, schemes, emphasizing their critical role in the smart grid's consumption side. Its primary goal is to make electricity consumption smarter and more efficient through systematic coordination of appliances and local distributed energy resources, DER. The main benefits are reduced electricity bills, decreased peak demand, and decreased peak average ratio, PAR. Pricing schemes are based on the analysis of tariff models such as real-time price, RTP, time of use, TOE, slanted block rates, IBR, and critical peak price, CPP. HEM schemes are categorizing into two types, communication-based, and optimization-based. The diagram shows the distribution of the equipment in a HEM system. Regional transmission organizations, RTOs, independent system operators, ISOs, and distribution system operators, DSOs, provide the global authority for the movement of energy. Their role is to optimize transmission and generation assets from both reliability and economic perspectives for the large transmission system footprint they operate. They economically dispatch the generators located in their footprint, monitor and analyze reliability on a near real-time basis, and provide the market mechanisms that will ultimately encourage consumers to participate in the electricity markets. Integration of smart grid applications at the distribution level. With these applications would enable the transmission system to utilize the distribution system as an asset to further optimize transmission and generation assets and their operation. Operators have learned a lot by implementing their reliability and economical dispatch programs. The integration of their experiences, processes and technologies with smart grid technologies and applications has opened new opportunities to optimize both transmission and distribution assets. Some of the services provided by RTOs, ISOs and DSO include Security Constrained Economic Dispatch, SCED, Locational Marginal Pricing, LMP, Markets, Day-Ahead Forecasting and Scheduling, Ancillary Services, Regulation Services, Reserves, Demand Response Capacity Bidding, etc. Wide Area Monitoring Systems, WAMS. The North American Synchrophaser Initiative, NASP, is a project to provide real-time monitoring of the nation's bulk power system. Wide Area Situational Awareness, WASA, new visualization tools to improve grid management automation and situational awareness, thus improving reliability and efficiency, and new system analysis tools, applications that support short-term and long-term planning, what-if analyses, and other analytical tools needed to support optimal operations. For decades, one of the key places to add intelligence to the power grid was the substation, primarily at the transmission level. After demonstrating the value of sending intelligence to substations, utilities established long-term transformation plans for their substation fleet. Substation Automation, SA, provides critical transmission-level information to support the analysis and optimization of transmission and distribution assets. Substation automation intelligence typically includes incorporation of intelligent electronic devices, digital relays, controllers, multifunction meters, etc., substation local area network and host processor, data concentrators and warehousing of real-time and event data, connectivity models and device attributes, communications to integrate substation-level intelligence with grid operations and RTO applications, user interface, remote and local, and condition monitoring sensors. The graph illustrates the linkages between the smart grid vision, key technologies and applications, and how system assets and utility processes can be optimized. The smart grid key success factors, KSFs, define where the smart grid will create value as its principal characteristics are achieved. KSF value areas include expected improvements in reliability, economics, efficiency, security, environmental friendliness, and safety. The first three milestones directly influence hard asset optimization, and the advanced asset management milestone integrates network intelligence to leverage the performance of key enterprise business processes that influence long-term asset management. Smart grids, optimization. When smart grids were created, their importance was compared to the Internet, and that it could give rise to new Googles and Microsoft. History was right. Customer engagement and the integration of new technologies are the key features. With network optimization, we can find the perfect balance between reliability, availability, efficiency, and cost. Network optimization spans from generation to transmission and from distribution to the end user. All of these are based on key smart grid technologies, namely integrated telecommunications and sensing and measurement. Key characteristics of smart grids: enabling informed participation by customers, enabling new products, service, and markets, accommodating all generation and storage options, provide the power quality for the range of needs in the 21st century economy, optimizing asset utilization and operating efficiency, addressing disturbances through automation, prevention, containment, and restoration, operating resiliently against various hazards. The transformation from the traditional grid to a smart grid is based on grid optimization. Develop the perfect balance among reliability, availability, efficiency, and cost. Demand response and demand-side management. Incorporate automated mechanisms that enable utility customers to reduce electricity use during periods of peak demand and help utilities manage their power loads. Advanced utility control, monitor essential components, enable rapid diagnosis and precise solutions. Energy storage, add technology to store electrical energy to meet demand when the need is greatest. Plug-in hybrid electric vehicle, PHEV, smart charging and vehicle-to-grid technologies, enable electric and plug-in hybrid vehicles to communicate with the power grid and store or feed electricity back to the grid during periods of high demand. Advanced metering, collect usage data and provide energy providers and customers with this information via two-way communications. Home area networks, allow communication between digital devices and major appliances so customers can respond to price signals sent from the utility. Renewable energy and distributed generation sources, reduce greenhouse gas emissions, provide energy independence, and lower electricity costs. Distributed generation sources. Small scale, usually in the range of 3 kilowatts to 10 megawatts, examples, wind turbines, solar systems, photovoltaic and combustion, geothermal energy production, and fuel cells. Distributed generation sources. Small scale, usually in the range of 3 kilowatts to 10 megawatts, examples, wind turbines, solar systems, photovoltaic and combustion, geothermal energy production, and fuel cells. Integrated communication. Broadband over power lines. Monitors and smart relays at substations. Monitors at transformers, circuit breakers and reclosers. Bidirectional meters with two-way communication. The diagram presents an energy storage system on a smart grid. Benefits. Shift load from peak hours to off-peak hours. Improve asset utilization of existing infrastructure, reduce investment required for new power plants, reduce investment to increase transmission and distribution limits. Transfer lower cost to end users, improve power quality. Frequency regulation, with fast spinning reserve, about 10 minutes, grid energy storage can quickly meet the increased demand. Voltage control, grid energy storage supplies reactive power too, which helps maintain satisfactory voltage profiles. Smart grid optimization is about making the power grid the best it can be. It's necessary to find the perfect balance between reliability, availability, efficiency and cost. To improve the utilization of current infrastructure and defer investments in new generation, transmission, and distribution facilities. To reduce the overall cost of delivering power to end users. To improve the reliability of power grid. To reduce resource usage and emissions of greenhouse gases and other pollutants. The facts are: optimization techniques have been used in the electrical industry. Many known optimization issues include unit compromise, voltage control, and feeder configuration. In general, optimization has been applied from electricity generation to end use. Decision-making artificial intelligence, DMAI, is the engine that transforms conventional electricity grids into smart grids, enabling the transition from a unidirectional flow of energy to a dynamic, bidirectional, and self-adaptive system. The pillars of DMAI address three critical challenges in managing the smart grids. Demand and load forecasting. Deep learning algorithms analyze historical patterns, such as weather and user behavior, to predict demand peaks with greater than 90% accuracy, avoiding overloads. Integration of renewable energies. DMAI compensates for the intermittency of solar and wind energy by optimizing power distribution and the use of energy storage systems, based on advanced weather forecasts and complex optimization algorithms. Demand-side management. Automated systems incentivize users to shift their consumption to off-peak hours through dynamic real-time pricing, achieving cost reductions of up to 20 to 30%. High-power smart grids. Optimization. Hypothalamus artificial intelligence, HI. Engineering projects for companies in the process of digital transformation. It presents its solutions and professional services based on decision-making artificial intelligence. Designed to optimize planning and operation in organizations in the electric and gas sector, using MOS mathematical models as a services. This enterprise-wide optimization system, EWOS, is called high power. The video introduces the detailed features of high power. HI has more than 50 years of experience solving problems for companies in the energy sector using models based on decision-making artificial intelligence. Electricity system and wholesale market optimization models make up a flexible decision support system that provides different types of services in an integral way. They can be classified into integrated dispatch of generation plants, optimization of generating agents, and predictive analytics of stochastic processes. The image, produced by IBM, presents opportunities for optimization along the electricity supply chain. The models and services offered by HI are aimed at supporting the decisions of companies and organizations in the electricity sector, either through simple mathematical models, traditional decision support systems, and/or business artificial brains. These include optimization of dispatch of electricity and gas systems and markets, energy trading and risk management, energy efficiency optimization, evaluation of energy projects, smart grid optimization, regulatory affairs modeling, electrical asset maintenance, and software factory. HI power is built following the principles of structured mathematical modeling, which are specific to optex. Under this conception, software is built by means of layers of equations, which are integrated to build the models, which are part of a decision support system. In the case of HI power, it is an economic dispatch model, typical of the electricity sector. The diagram shows 8 of the many models available at HI power. Any of the models can be run in their deterministic or stochastic version, making use of asynchronous parallel optimization. HI power is a decision support system that has been developed to support the decision-making processes of agents participating in the electricity and/or natural gas markets. HI power is composed of a set of optimization models that describe the supply/demand process of electricity and natural gas. From this point of view, it determines the partial equilibrium point of the electricity and gas markets under conditions of economic efficiency. Smart grids are the future of the electricity sector. Its impact is of immeasurable dimensions, considering the impact of the Internet. Smart metering measurement systems are the way to collect large volumes of information, big data, necessary to capture the added value of this new dimension. Demand has become an active agent, leaving aside the passive position it has maintained until now. The mathematical models used to optimize large power grids need to be revised considering this new environment. HI SGO, Smart Grids Optimization, corresponds to a set of mathematical models aimed at supporting the decisions of the agents participating in smart grids. It is made up of the following models: optimization of demand response, optimization of electrical energy management in building complexes, such as universities, housing estates, shopping centers, etc. Optimization of energy efficiency, optimization of electrical energy management in industrial systems intensive in energy consumption. Projection of availability of renewable energy sources, short/medium-term prediction of the availability of renewable energy sources, such as wind, solar radiation and water resources. Load management optimization, electrical load management optimization. Phase balancing and voltage management. Distribution network planning, optimization of the design of smart grids of the operation, based on its reconfiguration. Electricity theft detection, electricity network fraud detection systems, and real-time optimization, advanced control systems for optimizing the operation of a smart grid. HI SGO is composed of forecasting models and optimization models aimed at supporting the decision-making of electric agents smart grids, optimization of the economic and technical aspects related to smart grids in electricity companies. Demand response for buildings and/or housing, demand response, optimization of energy management in facilities, such as universities, shopping centers, office buildings, homes, urbanizations, and small towns. Industrial energy efficiency, optimization of energy management in heavy industries intensive in energy consumption. Forecast renewable energy sources. They correspond to predictive analytics models focused on the prediction in the specific sites where are located the generation plants. Models are also affected by the timing of the prediction. Forecast of demand energy. Long run. Demand projections per weeks, energy and maximum power. Medium term. Demand projections per weeks, located in medium areas. Short term. Demand projections per days or hours, located in specific installations. Real time. Demand projections per fractions of hours, located in specific installations. High SGO is integrated by the following optimization models. Economic/regulated dispatch of the smart grid, optimization of the management of electrical energy in small cities, factories, universities, shopping centers, office buildings, urbanizations. Smart grid unit commitment, optimization of the short-term optimization of the electrical load in real time. Smart grid configuration, optimizing the network topology, it considers voltage control, configuration of feeders, location/activation of electrical assets, transformers, capacitors, and phase balancing. Smart grid design, optimization of the design and/or redesign of smart grids with modern power technologies. ETRM, electricity trading and risk management, decisions to buy and/or sell electricity in a long medium short-term market, 1 day in advance and the day of dispatch. Industrial energy efficiency. The technical economic viability of energy storage coupled with the proliferation of energy technologies based on renewable energy sources has changed the landscape of the industrial sector, since it is now possible, and increasingly efficient, to generate renewable energy and store it for use in due time. This implies the tendency to standardize the marginal costs of generation around an average value for all periods and all the nodes of the electricity grid, capturing the benefits that this entails. In practice, all industrial companies can be agents that interact in the electricity market, since it is possible for all to act as co-generators and carry out commercial activities and transactions. This, together with the Industrial Internet of Things, increases the pathways to achieve industrial energy efficiency. Industrial energy efficiency results of the integration of production processes, transformation of matter, with industrial energy services, energy transformation, aimed at the simultaneous optimization of both industrial production and energy conversion that is related to polluting emissions of gases and liquids, associated with increasingly demanding environmental control laws. The high-power and high-SGO models can be integrated with complex industrial process models, in which it is necessary to redesign the power supply system according to the new power technologies. This type of model includes the simulation of polluting processes, for example, combustion in furnaces, to determine the optimal mixture of fuels in accordance with environmental regulations. High power and high SGO integrate the models and information systems around a common data model, allowing models to be connected automatically through the database or through RAM memory, integrating them as an artificial hypothalamus for an electricity company of wide coverage. Remember, all science as it grows toward perfection becomes mathematical in its ideas. Alfred Whitehead. Thank you very much for your attention.